First, two blocks with mass m1 and m2 are connected by a light string on frictionless horizontal surface. A horizontal force F is applied to one of the blocks, causing the system to accelerate forward with a constant acceleration. Find the tension in a string between the two blocks. So for this question, I will teach you a method called whole, then separate method. Basically, what this method is about is first, find the value that you need by analyzing the entire system. For example, in this question, it's a two-block system. After you find the value, you can plug that value back to one of the object or analyze only one object and then got the correct answer. If you think this method is a little bit, hard to understand literally, after I show you this question, after I explain you this question, you will feel like, oh my god, this is so easy. So let's begin. First, there's an F over here, right? Causing the entire system to move forward with constant acceleration. So first, let's write a net force equation. F is equal to, since we treat the system as an entire object, like a very big object, so there's no internal forces between them. So let's see what forces is act on the entire system or this big object. Only F, right? Also, there's no friction, so we don't need to write friction over here. So it's only F. It's equal to ma. What is the mass of this big object? It's easy, right? It's just a sum of the two objects. So sum of the mass of the two objects is equal to m1 plus m2 times a. And then we can get the acceleration for the entire system, which is equal to F over m1 plus m2. After we find the acceleration, after we analyze the entire system, the next step is to plug in to the separate part. So the entire system is moving forward with the acceleration F over m1 plus m2, right? Which means each of the single object are also moving forward, accelerating with this much of acceleration. So let's analyze m2. No, wait. Actually, let's analyze m1 because it's easier. So let's write a net force equation for m1. Net force m1 is equal to, what force is act on this single object m1? Ft, right? It's equal to Ft. And it's equal to m1 times a because we're analyzing the single object over here. So then you can find Ft just by plug a to the acceleration over here. So now let's find Ft. Ft is equal to m1 times F over m1 plus m2. So this is your answer. This method is actually very helpful when it is asking you the internal force or asking you the internal force in the question. So keep in mind. A mass m is suspended by two strings that make angles alpha and beta with a ceiling. The system is in equilibrium, which means they're completely at rest. Find the tensions T1 and T2 in the two strings. First, let's draw a free body diagram. There obviously gravitational force that act on it which is Fg. And both T1 and T2 are act on it. Let's say this is T2. Because imagine this rope is pulling it to that direction. This is T2. And then this is T1. So this is our free body diagram over here. And then because it's at equilibrium, which means it is completely at rest, which means both net force on x direction and the net force on the y direction are equal to 0. Now, let's separate them into parts. If you're wondering which angle is alpha and which angle is theta, imagine this is a ceiling. I already tell you this is alpha and this is beta, right? Since this and this are parallel, we can easily get this is alpha and this is angle beta. Also, I already told you the value over here. Alpha is 30 degrees, beta is 45 degrees. Of course, you can write alpha is 30 degrees and beta is 45 degrees. It's your choice, but I love writing letters first. And now let's separate them. Or break them down into components. So first, let's write the net force on x direction. They're this force component and this force component, which you can write, what is this force component? Is T1 times cosine alpha, which is, and then minus T2 times cosine beta, which is equal to 0. Now let's write the net force equation for the y direction. Let's look at the graph. On the y direction, there are three forces, three components. One is over here, the other one is over here, and the final one is just the FG. Also, one thing that's worth mentioning is that this component is pointing upward. This component is also pointing upward. However, FG is pointing downward over here. So let's write it down. Using trigonometry, we can get T1 times sine alpha plus T2 times sine beta minus mg, or fg, I would just write mg here, is equal to 0. So now we can solve the equation. As you can see, there are two variables over here, or unknown variables over here, and there are two functions, which means you can definitely get a unique number pairs for T1 and T2. So for me, personally, I would just plug the number in over here. So T1 times cosine, wait, let me put the number out. Cosine 30 degrees minus T2 times cosine 45 degrees is equal to 0. T1 times sine 30 degrees plus T2 times sine 45 degrees minus m, what is the mass of the object? 5 kilograms. Minus 5 times, I'll use 10 as g here. 5 times 10 is equal to 0. So after you use your calculator, you can get something like T1 is equal to around 36.6 newtons, and T2 is equal to 44.8 newtons. So this is your answer. A negligible mass has an unstretchable string passing over it. The two ends of the string are attached to mass m1 and m2, where m2 is bigger than m1. Neglect the friction between the pulley and the string. A. Find the acceleration of the system. For this question, we're still using the whole separate method. One thing that you should keep in mind in this question is that the tension force between them are the same. For example, on M1, there's a tension force that's pulling it upward, right? It's equal to the tension force that is pulling M2 upward. So first, let's write a net force equation for the entire system. Net force is equal to, there's a gravitational force that acts on M2, right? So let's write M2G minus Ft, right? Because Ft is pointing upward, plus Ft. Although this Ft is also pointing upward, it is pulling M1 upward, so it's actually cancel out the resistance force that allow M2 to go downward. So we can write plus Ft minus M1G. Since M1 is resisting M2 to go downward, so we write M minus over here. So this is equal to, these two can cancel out, right? And then we can just simplify it to M1 plus M2 times G. Wait, M2 minus M1, my bad. And it's equal to the total mass, which is M1 plus M2, right? Or I should write M2 plus M1 times the acceleration, which we can get A is equal to M2 minus M1 over M2 plus M1 times G. This is your acceleration. B part. Find the tension of the spring. You can pick either of the object. You can pick M1 or M2. Over here, I will pick M1. B. The net force for object number 1 is equal to, there's a mass pulling it downward, right? And there's a tension force pulling it upward. Since you can imagine, because M2 is bigger than M1, so it's definitely sliding down this way, right? So the tension force over here is definitely bigger than the gravitational force of the object number 1. This is very important because it can ask you to draw a free body diagram, and you must draw the tension force is bigger than the gravitational force. You understand it? Okay, so let's write it. It is equal to Ft minus M1G. And this is equal to M1 times A. We can plug the A we already got over here. And then we can get Ft is equal to M1G plus M1 times, well, let's write M1 times G. You can easily figure it out if you learn algebra 2 or even algebra 1, because I literally just put G to the front. M1G times M2 minus M1 over M2 plus M1. So this will be your answer. Or I can analyze it using the second object. Ft is equal to M2G minus Ft is equal to M2 times A. you can get Ft is equal to m2 times g minus a, which is equal to m2 times g times this one's supposed to be 1 minus m2 minus m1 over m2 plus m1. You can see that these two are different, right? But if you can plug in the value will be the same. For example, if I told you that m2, m1 is equal to like 1 kg and m2 is equal to 2 kg, you can get Ft from the first expression. You can get something like 10 plus 10 times 2 minus 1 over 1 over 3. You would get something like 13.333, and plug in number 2, you would get something like 220 times 1 minus 1/3, which is 3 over 40. You will also get something like 13.333. So both of these expressions are correct. On your test, it will usually give you a number, so it will not make you confused. A block of mass m1 rests on a horizontal surface at the edge of the surface. A mass negligible fixed pulley is installed. It's installed over here. A light unstretchable string passes over the pulley, connecting the block m1 on one side and hanging mass m2 on the other side. A part. If friction on the surface is neglected, first, find the acceleration of the system. Second, find the tension of the spring. So for this question, again, we're using whole separate method. As you can see, this method can actually fit in a lot of scenarios in physics problems. So let's solve it. A. Let's write the net force equation for the entire system. F. So for block M2, right, it's pulling it downward. And then there's a tension force that resists it from going down, right? And for M1, there's a tension force that is equal to the magnitude of tension over here. And this tension is pulling it, it's like help it to move along the surface. However, also if there's friction, the friction will be like resisted from going along the surface. So let's write, so the net force is just m2g minus ft plus ft. Since there's no friction over here, we can just leave it blank. So this is your net force, and it's equal to the total mass times A, which is m1 plus m2 times A. And then you can get the acceleration, which is A is equal to m2g over m1 plus m2. This is the first part. On the second part, find the tension in the string. For the first part, you already got acceleration is equal to m2g over m1 plus m2. Now, let's use the separate part in a whole separate method. Let's analyze mass 2. Write the net force equation for it. this is equal to, there's a gravitational force that grab it, pulling it downward, right? And there's a tension force that pulling it upward. So the net force will just be m2g minus ft is equal to m2 times a. And you'll get f2. ft is just equal to m2 times g minus, no, yeah, m2 times g minus a times g minus a. And then you can plug the acceleration to here. You will get ft equals m2g times 1 minus m2 over m1 plus m2. This is your answer. Now let's look at B part. If friction on the surface is not negligible and the coefficient of the kinetic friction is mu, find the acceleration of the system. 2. Find the tension in the string. Although there's friction here, but you don't need to worry about it because I got you. It's basically the same thing, but just a little bit, complicated, only a little bit. So first, still using whole separate method, we can write the net force equation for the entire system, which is m2, right? m2 going downward, and there's the ft pulling it upward to resist it from going downward. And then for m1, there's a ft pulling it to move along the surface. However, this time we got a friction, which is pulling it backward. So we can write m2 minus ft plus ft minus ff. We can simplify it first, which is equal to m2 minus ff. And it's equal to m1 plus m2 times the acceleration. Since over here, ff is caused by m1, as we know, the function for friction force, is equal to Fn times mu, right? And then over here, since the mass 1 is not moving upward or downward, which means it is at equilibrium vertically, which means Fn is just equal to Fg. Since the net force vertically is equal to 0, there's only gravitational force and normal force act on it, which means these two are equal. So Fn times mu can be written as Fg times mu, and is equal to m1g times mu. Let's plug it to here. Then we will get m2 minus m1g times mu is equal to m1 plus m2 times a. And we can get a is equal to m2 minus m1g times mu over m1 plus m2. This is your answer. Not that complicated, right? Now, second part. Find the tension in the spring. For the first part, we already got A is equal to, if I remember it correctly, is equal to m2g minus m1g times mu over m1 plus m2. And then let's do the separate part in a whole separate method. Let's analyze the mass number 2 again because it's just easier. the net force for your mass number 2 is equal to m2g minus ft because they're pointing in opposite direction, right? And it's equal to m2a. We can plug a over here, and we can get ft. First, let's move ft to one side of the function. We can get ft is equal to m2 times g minus a. And then you can plug in the acceleration over here. Then you can easily get ft is equal to m2g times 1 minus m2 minus m1 times mu over m1 plus m2. This is a simplified version. You can easily get that after you simplified like the complex version when you plug a to the formula. So this is your answer. It's not that hard, right? It's very easy. You got this. A mass m rests on the horizontal surface. A force of magnitude F is applied to the object at the angle theta above the horizontal. The coefficient of the kinetic friction between the object and the surface is mu. Find A. The normal force exerted by the surface. B. The magnitude of the frictional force. C. The acceleration of the object. D. If F or Ft becomes large enough, the object may lose contact with the surface, which means the object will like fly or yeah. To maintain the minimal contact, what is the maximal value of Ft? So let's solve A part first. When you're solving this type of question, the first step you need to do is to draw a free body diagram. It's very important. So let's do it. These points represent the center of mass of the object. Since it's on Earth, there's definitely gravitational force that pointing straight down. This is Fg. Also, because this object is on horizontal surface, right? So there's definitely normal force that applied by the surface, and the normal force will always be perpendicular to the surface that the object is contacting with. This will be the normal force. You may ask, why Fn is smaller than Fg over here? You will figure it out after I explain it to you, but don't worry about it right now. There's an Ft that pull the object to that direction and creating an angle theta above the ground. So we should also draw the Ft on the graph. I would say this is Ft. Since the Ft is pulling the object moving that direction, and the friction is not negligible in this question over here, which means there's definitely friction force appears in this question. The friction force will be pointing that way since it is opposing the direction of the movement. So let's also draw it on the graph. One thing in this free body diagram that you should keep in mind is the magnitude of the vector of ff must be smaller than the magnitude of the fn, since fn is equal to mu. Wait, that's not right. Ff is equal to mu times fn, right? And then mu will be always smaller than 1. So ff will be always smaller than fn. This is very important. If you didn't draw it correctly in your exam, your teacher would definitely not be nice to you. Okay, let's keep on going. First, the normal force exerted on the surface. Since the object is only moving along this direction, right, or the horizontal direction, it is not moving vertically. There's no movement vertically, so which means the net force on the vertical direction is equal to 0. So right now, what you need to do is to find the components on y-axis or vertical direction. So what you need to do is to break them down. Do something like this, right? So as you can see, this is theta, right? Since it's creating an angle with a horizontal surface. So this is theta. So now you can write something like, I'll write it over here, I guess. The net force on the vertical direction is equal to Fn plus Ft times sine theta minus Fg is equal to 0. So now it can explain that why on the free body diagram Fn is smaller than Fg, since Ft times sine theta is also on a vertical direction, which means this part of the vector plus Fn is equal to Fg. So Fn must be smaller than Fg in this scenario. So now we can find Fn. Fn is simply equal to Fg minus Ft times sine theta. What? Now for the B part. From the last question, we figured out Fn is equal to Fg minus Ft times sine theta, which is equal to mg minus Ft times sine theta. We know that the friction force is equal to Fn times mu. Since mu is already given you in the questions over here, which means we can directly use it, we can directly plug it to this formula. So now let's just plug Fn, the expression of Fn, to the friction force formula and find out Ff. So Ff is simply equal to mg minus Ft times sine theta times mu. Simple. Now let's do the C part. Find the acceleration of the object. The acceleration is pointing that way because of the horizontal components of Ft. However, there's also friction force that resisted from moving that direction. So we can now write the net force equation out for the horizontal component of the object. Fx is equal to, my suggestion for writing this equation is always write the big force first. For example, since it is moving that way, right? Since it is accelerating that way, which means the components here is definitely bigger than the FF. If it is smaller than or equal to, it will not be equal to as actually. If it's equal to, it will just remain constant, right? So let's write it down. It is equal to Ft times cosine theta minus the FF over here. I'll just plug in the FF you already saw from last part minus uh, mg minus ft times sine theta times mu. And this is equal to ma. So this is what you want to solve. So we can just simply divide it, m on both sides, which we can get a is equal to a is equal to ft times cosine theta over m minus g mu plus ft times mu sine theta over m. After simplify it, I love simplify equation because it looks much better. We can get ft over m times cosine theta plus mu sine theta minus g times mu. And this is your answer for the C part. Now let's solve the D part. If f becomes large enough, the object may lose contact with the surface. To maintain minimal contact, what is the maximum value of ft? So for this question, what I would do is first analyze the words in the question. The object may lose contact with a surface. So imagine if ft is like very big, it will literally just like flying, right? Lose contact. So I can say that if ft is large enough, the fn will no longer exist because when the object is like flying, is it contacting with the surface? No. So fn will be 0. To maintain a minimal contact, what is the maximum value of ft? So this is our thought process. Write an equation where there's this no fn. However, it is still like barely a contact with the ground, which means the net force vertically is still equal to 0. And then we can find ft. So let's do it. So in this also in this situation, the free body diagram will look like this. Fg. There's this no normal force. This will be Ft. That's it. Also, there's no friction force since there's no normal force, right? Normal force is equal to 0. And so Ff is also 0. So now let's separate them into components. This is angle theta. Since I can say that it still have like minimal contact, right? So I can write Fy net force Fy is still equal to 0 because it almost lost contact with the surface. However, it still hasn't. So it's like it is not moving vertically yet. It hasn't moved vertically yet. So we can write net force on the y direction is equal to 0. So now let's break them down to components. Net force y is equal to, using trig, we can get Ft times is that sine theta is equal to, no, minus mg equals 0. We can get Ft is equal to mg over sine theta. So this will be the maximum value of the ft. If the value of ft is bigger than this value, the object will lose contact and start flying in the sky. Or in the physical form, the object will lose contact with the surface and start moving vertically, which means the net force on the y direction will no longer equal to 0. A block of mass m slides down an inclined plane that makes an angle theta with the horizontal, reaching the bottom after time t. A. Neglecting the friction between the object bottom and the incline. What is acceleration of the block? What is the length of the incline? So now, what is the first step of doing this type of question? Yes, you're right. Free body diagram. Good job. So let's do it. This represents the center of mass of the object. Of course, there's gravitational force that act on the object. Since the object is on the surface that go like this, which means the normal force will always be perpendicular to the surface that it is contacting with. So the normal force will be pointing that way, around about that, Fn. So now let's break them down to the components. For this type of incline question, I will always suggest you to separate them, not using the regular x and y direction, however, using the direction that is along the incline. So the reason why the object is moving downwards is because there's a component over here that is pulling it downward, right? So the only thing we need to do over here is to find this component. And using Newton's second law, we can get the acceleration. So this is one of the components. Always remember this angle with a theta in AP1. You don't really need to worry about it right now. And yeah, this is theta, and we can get this component. Wait, this component is equal to mg times sine theta. Now let's write the net force equation for the direction along the incline, which is this direction. We can write something like net force Fx along the incline is equal to mg times sine theta, and it is equal to ma, which we can get a is equal to g sine theta. That is your answer. And second part is find the length of the incline. Also, I need to state that the block is originally at rest. So using your kinematic equation, using x is equal to v naught t plus half at squared. It's initially at rest, right? So there's no v naught t here. So there's only acceleration and t. So we can get x is equal to half times g squared times sine squared theta. Also, if you're not that good in algebra, don't write second power here because it will be theta's second power, not the sine theta to the second to the squared, and times t squared. If you want, you can simplify it as half times gt sine theta squared. This looks better, and this is your answer. Now let's keep on going to the B part. With friction on the incline, coefficient of friction equal to mu1. 1. What is the acceleration of the block? 2. What is the length of the incline? So, still, draw a free body diagram. This represents the center of mass of the object. This is a gravitational force. Oh, this is a gravitational force, Fg. And also, there's definitely normal force that acts on it that is perpendicular to the surface, right? So this is a normal force, Fn. However, right now we got friction force, so we cannot neglect it. So this is your friction force, Ff. Let me mention it again. When you're drawing the free body diagram, draw Ff in magnitudes. When you're drawing the vector of the friction force will always be smaller than the vector of the length of the vector of the normal force. So this is your free body diagram, and now let's break them down to components along. Alright, it will look like something like that. This is your theta. So the only force that is not in components is the Fg, because other forces like Fn and Frf are all along the direction of the incline or be perpendicular to the incline. So let's break Fg to component. This is your horizontal components along the direction of incline. This is your vertical components relative to the slope. And then you can write the net force equation since the block is not moving upward or downwards vertically relative saying to the incline. We can get something like net force Y is equal to Fn minus Fg times sine theta. Wait, no, cosine theta is equal to 0. We can get Fn is equal to Fg times cosine theta. So after we find Fn, we can easily get the friction force over here, right? Since Ff is just equal to Fn times mu. So we can easily get Ff is equal to, this is supposed to be lowercase f. It's just simply equal to Fn times mu is equal to Fg times cosine theta times mu. After simplifying it, we will get mg times mu times cosine theta. I forgot there's a theta here. So this is your friction force. So now we already figured out every component along the slope direction, which means we can now write the net force equation for the direction of the incline. Net force Fy is equal to this component minus Ff. Using trig, we can get this component over here is equal to Fg equals mg times sine theta minus your Ff. I think I'll just write Ff straight down here. It is equal minus mg times mu times cosine theta equals m times a. Mu equals mu1. I forgot. So you can get a is equal to g times sine theta minus mu times cosine theta. This is a simplified version, but after you simplify the equation, it will look something like this. So don't need to worry about it, because I think it just looks better. So now we find the acceleration, right? What is the length of the incline? We're doing exactly the same thing as the last part. D is equal to V naught t plus half at squared. V naught is 0 initially, right? Because it's at rest. So it's just simply equal to half at squared. Then we just plug A over here straight down here, we can get D is equal to half times T squared times A, no, times G sine theta minus mu 1 times cosine theta. And this is your answer for this part. C. The incline has a friction of coefficient of mu1. After reaching the bottom, the block continues onto a horizontal surface with a friction mu2, with the block smoothly transitioning to the horizontal surface so that its velocity at the bottom of the incline becomes the initial velocity on the horizontal surface. Find the sliding distance on the horizontal surface. So it is smoothly transitioning, right? So we don't need to worry about something like the block will be stuck at the bottom, so it will lose its velocity, yada yada yada. So we don't need to worry about it. Just remember, when the block is at the bottom, the velocity is the same. It's like this, exactly the same as the initial velocity when it start moving on a horizontal surface. So first, we need to find the final velocity after as soon as it reached the bottom of the incline. So Vf is equal to V naught t plus half at squared. The V naught is equal to 0, right? So there's no V naught here. So we can just figure out Vf by plugging acceleration to the function so that we can get Vf is equal to half g times t squared times sine theta minus mu 1 cosine theta. This is the final velocity. Then it smoothly transition to the horizontal surface. So now let's draw a free body diagram for the object when it's moving on a horizontal surface. So this is the block, right? It represents the center of mass of the block. Of course, there's gravitational force. Now it is on the surface, so its normal force will be perpendicular to the surface, which is straight up. In this scenario, it's straight up. And since the block, after it slides down the slope, it is moving that way, right? So its friction force will be always opposing the direction as it's moving, so it's going that way. This is the friction force. This is a normal force. In this scenario, since the object is always it's not moving along the vertical direction. It's not moving vertically, right? Because it's only moving horizontally. So over here, Fn is equal to Fg. Or I can write Fy is equal to 0 equals Fn minus Fg equals 0, which we can get Fn equals mg. Because Fg is equal to mg, right? And then we can get the friction force, Ff, which is equal to Fn times mu. Right here is mu mg. Mu times m times g. And now let's write a net force equation for the horizontal surface. Since it is moving horizontally and we must figure out when it stopped, right? We can find the acceleration by writing the net force equation for the horizontal direction. We can write net force Fx is only equal to Ff, which is equal to m times a2, because we cannot use a here because a we already being used. It's already being used, which we can get a2 is equal to mu2 times g. Because the coefficient of friction on a horizontal surface is equal to mu2. So we will write mu2 over here. So now we figure out the acceleration. We know the initial velocity, which is over here. So we're trying to find the distance it travels. We can use a formula v squared equals v naught squared plus 2ax. Since the object comes to the rest at the end, so v is equal to 0. So negative v naught squared is equal to 2ax. Now we can find x, which is equal to negative v naught squared over 2a. However, over here it's asking you the distance, which means it must be positive. And v naught squared is positive, right? And 2a, we can just plug in the magnitude, which is also positive, so that x distance is actually equal to positive 2a v naught squared. And now it's time to plug in a value. This is vf, which is equal to v naught over here, since the final velocity when the block reaches the bottom of the incline is equal to the initial velocity of the block when it starts moving along the horizontal surface. And a, which is equal to mu2 times g, we can get x is equal to, this is a little bit complicated. A quarter of g squared times t to the fourth power times sine theta minus mu1 cosine theta. One sec. Times 2 mu2 times g. 1 over 2 mu2 times g. We can cancel out one of the g. So the final answer will be, I need a ruler to draw the fraction line because it looks better. This is definitely a lot of fraction line. We'll get something like 8 mu2 on the denominator, and on the numerator we'll get g times t to the fourth times sine theta minus mu1 times cosine theta. And this is your answer for the last part. On the actual test, I think for AP1, your teacher will usually give you the numbers, so you really don't need to find like the expression, but I still highly recommend you to do it and to understand it because it can improve you by a lot. Now, the last one. A block with a mass m moves along an inclined plane that makes an angle theta with the horizontal, a constant force F x along the plane. The block was forced to a complete stop after time t. A. Neglecting the friction, find the magnitude of the displacement along the incline d1. So, what's the first step of doing this type of question? I forgot. Oh, good job, you remind me. It's a free body diagram. Good job. So, this represents the center of mass of the object. Of course, there's gravitational force acting on it, which is Fg. The normal force will always be perpendicular to the surface it is contacting with. This is a surface. This is your normal force. No friction force in the A part, so we don't need to worry about it. And there's the action force that is pulling it along the surface. This is action force. F. So this is still a type of incline question. Ah, it looks terrible, but let's assume it is perpendicular. So let's see. So for the horizontal direction along the incline, there are two forces or two components of the forces. One of them is the action force, and the other one is the horizontal components of the FG, and it is opposing the direction of this F. So we can write the net force equation. Net force Fx is equal to F. The bigger force always come first because it is moving along the incline, right? The bigger force always come first. F minus Fg. This is theta, by the way. Fg times sine theta. It is equal to ma. A. A. Okay, and then we can get A is equal to I'll make it look a little bit better. It would be F over M minus G sine theta. This is your acceleration along the slope, and then you want to find the displacement, right? After a time t. So x is equal to v naught squared plus half a t squared. Let's assume the block is also at rest initially. Yes, it is at rest at initial state, which x is just equal to half a t squared. So now let's just plug in the value. Plug in a directly to this expression. We can get x is equal to half times f over m minus g sine theta times t squared. I think it looks good, in my opinion. It already looks good, so I don't need to simplify it. Well, and then this is your answer. That's it. This is your displacement, the magnitude of displacement, actually. Now, the B part. With friction on the incline, coefficient of friction equals mu. First, find the magnitude of displacement along the incline, d2. 2. If the time is doubled, which means t is now equal to 2t, find the ratio of the new displacement d3 to d2. Assume the incline is long enough. Alright, let's begin. Oh, I forgot again. What's the first step of solving this problem? Yes, free body diagram. Good job. So, B part. I should move it a little bit to the right, to the left. Free body diagram. This represents the center of mass of the object. This is mg. I think you already realized that there's a normal force perpendicular to the surface. Fn. There's an action force. Action force F. And there is a friction, which is opposing the direction of the objects moving. So this is F. And the magnitude of FF will be always smaller than the magnitude of the Fn. So now let's solve the question. First step we need to do is to break them down along the slope and the direction which is perpendicular to the slope. Oh, it looks terrible again, but I think let's assume it's perpendicular. I don't have a ruler besides me. So the block is moving upward, right? So we should do a net force equation for the horizontal components, which is net force F x is equal to F minus this component over here. This component is pointing that way, and FF. So we can write it down. Minus mg. Also, this is theta. We can using trig we can get this component, which is mg times sine theta minus ff is equal to ma. M times a2 actually. It is not. It is not. It has. It doesn't have the same acceleration as the last question. And then we can write a net force. We don't. We cannot figure out the ff yet because we don't know the normal force. So let's write the net force equation out for the vertical component as well. Net force Fy is equal to Fm minus, using trigonometry, mg times cosine theta. It's a block. It's a block moving vertically upward or vertically downward relative to the slope. No, it's not, because it is moving along the slope. If you don't understand what this means, if you don't understand what I mean, moving vertically upward means that it's just like moving in that direction. It's like it's no longer have contact with a slope. So I think you understand what I mean. Uh, so this is equal to 0. We can easily get Fm is equal to mg cosine theta from this expression, and we can then easily get Ff is equal to mu times mg cosine theta. Now we already figured out Ff, so let's plug it back in to x direction. Net force Fx is equal to F minus mg times sine theta plus mu cosine theta. I just reformed it to make it look better, and it is equal to m times a2, which we can get a2 is equal to f over m minus g times sine theta plus mu cosine theta. What is the question asking you? Oh, it is asking for the displacement along the incline d2. So we can still use our kinematic equation. Wait, let me pull it a little bit downward. d2 will be just equal to v naught squared, v naught t, plus half at squared. V naught is equal to 0, right? So d2 is simply equal to half at squared. Let's plug the value in, which we can get d2 is equal to half f over m minus g times, let's write t squared over here, g times sine theta minus mu cosine theta. Mu cosine theta. And this is your answer for the first part of B. Now, if the time is doubled, find the ratio of the new displacement, d3 to d2. Assume the incline is long enough. This is actually free, because you already get the expression for the displacement along the incline of the object. So when the t is doubled, right, d3 will be equal to t, 2, t squared now became 2t squared, which is 2t squared times blah 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 times this long expressions. We don't need to care about this expression because there's nothing related to t. So d3. So now d3 will become 2t squared times this long expression, exactly the same. I'll just copy it down. So what is a numeral ratio between d3 and d2? This is simply d3 over d2. It's just equal to, I don't want to write it again, just 2t squared times, just 2t squared times this long expression over half t squared times exactly the same long expression, so that we can cancel these two out, right? Which will only become 2t squared. Wait, I should write it down. 2t squared over half t squared, which we can get the final answer 4.